A hot, molten metal. By heating this metal to a high enough temperature, we can change it from a solid to a liquid. That is, we can change its properties. Change in temperature is one of several different ways of changing the properties of a material. Once molten, the metal can be shaped by casting it in a suitable mould. This is a sand mould. It's made in two halves, each half containing an impression of the component we're going to cast. A ladle is often used to carry the liquid metal from the furnace to the mould. Before casting, the surface of the metal is skimmed to remove any impurities. There are 3 holes in the top of each mould. The metal is poured into only one of them. The other 2 are there to let the air out and to ensure that the metal completely fills the cavity inside. As the temperature falls, the metal solidifies. The change from solid to liquid was only temporary. The mould can be opened before the metal is completely cool. Separating the metal from the sand isn't always as easy as you might think. Casting is a process which depends on the use of heat to change the properties of a metal from a solid to a liquid. We can use heat to bring about other changes in the properties of a material. This piece of cold, mild steel isn't a very malleable material. It can't be hammered into shape very easily. All that effort and hardly anything to show for it. In this forge, we've heated a similar piece of steel until it's a bright cherry red in colour. That's well below its melting point. Let's see if that's made any difference. By raising its temperature, we've made it much more malleable. Steel is often heated to increase its malleability. This steel ingot is so hot that in this hydraulic press it can be forged quite easily into a new shape. Again, this change in property is only temporary. When the steel cools, it will become less malleable. However, by heating and cooling steel and certain other materials in a particular way, we can bring about permanent changes in their properties. These castings are made of one such material. They're lathe beds. In this cast state, material is relatively soft and easily machinable, so the large quantities of unwanted material can be removed by milling. Here we're machining one of the slideways. Now, in service, this part needs to resist wear and indentation. It must be hard, but in its present state, it's relatively soft, so now the slideway must be hardened. We do this by heating and then cooling the material in a carefully controlled way. First, the metal surface is heated to about 900 degrees centigrade, in this case by a row of high-temperature flames moving slowly along the slideway. The hot metal is then cooled rapidly with water. This heating, followed by rapid cooling, hardens this particular material. If we look at a specially prepared cross-section through the slideway, you can just see the hardened area around the edge. We can test this with a file. Here it's hard. But here, where the metal wasn't heated and cooled, it's still relatively soft. Once a material has been hardened, any final machining must usually be done by grinding. This process of heating and cooling certain materials to harden them is known as a heat treatment process. These overhead electric cables are made from aluminium, a pure metal which is light and a good conductor of electricity. But for overhead cables, aluminium lacks one important property: tensile strength, necessary to support their own weight. For this reason, there's a core of high tensile steel wires running through the cable. Just how strong is aluminium? In this machine, we can measure the force needed to pull materials apart. Here, we're pulling a piece of aluminium. The force is measured on this dial. It's going to fracture near the bottom. And the force, nearly 8 kilonewtons. Now we can increase the strength of the aluminium by adding to it two other materials: silicon and magnesium. First, we put into the molten aluminium a measured quantity of silicon. It's measured out by weight. After time, the silicon will dissolve. Then the magnesium can be added. We don't need anything like as much of this. Like the silicon, magnesium takes time to dissolve. This new material we formed is called an alloy. It's an alloy of aluminium. To find out how alloying has affected the strength of the aluminium, we must cast a suitable test piece. To compare forces, the alloy test piece must have exactly the same dimensions as the aluminium one we tested earlier. Now for the test. Well, that's where the aluminium fractured, but as the force is increased, the aluminium alloy proves to be much stronger. By forming an alloy, we've brought about a useful change in the mechanical properties of the aluminium. We've increased the tensile strength. But strength isn't the only property that's changed. When we put the broken bits back together, we'll find another. By comparing lengths, we see the pure aluminium stretched more than the aluminium alloy. This means the alloy is less ductile, so there's been a decrease in ductility. And what about the hardness? Let's see if that's been changed in any way. We can compare the hardness by pressing a steel ball into the surface of each material. This is the result with pure aluminium. Now we'll do exactly the same test on the aluminium alloy. This time the indentation looks much smaller. The smaller it is, the harder the material. So by forming an alloy, we've increased the hardness. Alloying is an important way of changing the properties of a material. One of the commonest alloys is steel. It's a material with many useful properties. Steel is an alloy of iron and carbon, two materials with only a limited number of useful properties. Take carbon, for example. It breaks very easily. It's weak and brittle. How about the iron? That bends very easily. It's a soft and ductile material. But an alloy of these two, steel, behaves quite differently. It's stronger, and it hasn't bent. Now, steel contains only a very small amount of carbon. In this piece of steel, there's only this amount of carbon. By weight, it's about 1,000th part of the steel. We say it's a 0.1% carbon steel. Other steels are produced which have a different carbon content. Here are 4 of them. What effect do you think the amount of carbon has on the mechanical properties of the steel? Well, let's find out. What we're measuring here is the force required to pull apart a piece of 0.1% carbon steel. We're measuring the force in kilonewtons. That fractured at 61 kilonewtons. 0.25% carbon steel. Let's see what force is needed to pull this one apart. This test piece has the same dimensions as the previous one, so by comparing forces, we can compare the tensile strength. Well, that's where the 0.1% steel fractured. Increasing the carbon seems to have increased the tensile strength. Nearly 80 kilonewtons this time. Let's put those results on a chart. The tensile strength of 0.1% carbon steel is this much. The one containing 0.25% showed a slight gain. Similar tests on the other two steels gave these results. 0.4%, even more strength, and 0.55% carbon, stronger still. So it seems that the more carbon there is in the steel, the greater the tensile strength. But what effect does increasing the carbon have on the other mechanical properties of the steel? Take hardness, for example. Here we're measuring the hardness of the steel containing the least amount of carbon. We're measuring its resistance to indentation. On this machine, reading on the inner scale, we have a hardness value of about 69 units. 0.25% carbon steel, (81 units this time. The higher the reading, the harder the material, so the hardness has increased. Here are those results on a chart. The same test on the other two steels showed a further increase in hardness. The more carbon there is in the steel, the harder it seems to become. At the same time, there's an increase in tensile strength. But what do you think happens to the ductility? Well, we'll leave that for you to find out. A cast copper billet. It's been heated to a temperature of about 700 degrees centigrade. At this temperature, copper is more malleable. It can be pushed through a specially shaped die. And made into a long and heavy tube. This process is known as extrusion. It's the first stage in the manufacture of copper tubing, the kind used by plumbers. Once the tube is cool, it's ready for the next process. With one end pointed, the tube is inserted into a die whose diameter is slightly smaller than that of the tube. The pointed end is gripped and the tube pulled through the die. This has the effect of reducing the diameter of the tube. It's a process known as drawing. In this cutaway section, you can see what actually happens. The tube is drawn over a steel plug and through the die. As it's pulled through, there's quite a reduction in its diameter. Also, you can see here how the thickness of the wall is reduced. Deforming a metal when it's cold like this is known as cold working. A tube is drawn more than once. Each time, both the diameter and the wall thickness are reduced. This has the effect of making the tube much longer. Since we started, we've reduced the tube to this diameter. There can be as many as 10 more draws before the tube is down to size. With each draw, the wall becomes thinner and thinner. In other words, each draw involves a lot of cold working. Well, after all that, have the mechanical properties of the copper changed? Let's find out. How hard is it? Remember, hardness is its ability to resist indentation. On this scale, it has a hardness value of 84 units. Let's compare that with the piece of the cast copper we started out with. It looks much softer. And from the reading we see it is only 62 units. We can see this difference in hardness by comparing the size of the two dents, cast on the left, drawn on the right. So cold working has had the effect of increasing the hardness of the copper. What effect has it had on the tensile strength? Here we're measuring the drawn or cold worked tube. We're measuring the force in kilonewtons. That fractured at 27 kilonewtons. Now, to compare tensile strengths, we must measure the force needed to pull a similar piece of cast copper apart. We need a cast tube. But of course, we can't cast a tube. What we can do, though, is machine one from a cast billet. Although this involves some cold working, it's nothing like the amount that's involved in drawing the tube. There. Now for the test. It's much weaker than the drawn tube. Only 6 kilonewtons this time. Since the tubes were the same size, this means that the tensile strength has increased. So cold working has not only increased the hardness, it's also increased the tensile strength of the copper. It's brought about two useful changes in its mechanical properties. But what if we try bending a piece of cold work tube? Not all its properties are useful ones. Can you think what could be done to the copper to prevent this from happening?